When adding vectors graphically, so such that you have 4 force vectors, vector A, which may be 10 newtons at an angle of 110 degrees, vector B, 18 newtons at 20 degrees. Remember, everything is measured from the positive x-axis. And vector C, negative 15 newtons at negative 30 degrees. Here's the 20 degrees, and I can kind of draw this one from the x-axis. So if this is 110 from the positive x-axis all the way over here, this would be 70 degrees. I'll go ahead and erase this 110 on here. So if we wanted to add all those vectors graphically, we would add them head to tail. You can kind of get a feel of where the resultant vector is going to be somewhere over here in this range going this direction, but probably a little bit further. So maybe right in here somewhere. So let's go ahead and see if we add them head to tail. So head to tail, the head of a vector is the point, and the tail of the vector is the end here. So we're just going to add them in a chain. It does not matter the order that you add them in. So we're going to go ahead and let's just start with vector A, and it goes up at about 110 degrees. Then we can go vector B at about 20 degrees. And then vector C goes down below the x-axis. So we're going to call that negative 30. It could have been called 330 degrees, but it's easier to think of it as negative 30. I'm just going to go down here. That is vector C. But you can see as we do them just in a big chain, and then we finally do our resultant vector nice and dark. And that is the final force. So if we have all of these forces, A, B, and C, acting on one object, then the resultant force is going to be forced to the right and a little bit upward. So this is going to be what we call our resultant vector. So we can do that mathematically as well. So you can really find out the value and the angle, because here, we could use a protractor, but it's really hard to see what the angle is and what the resultant magnitude of that is going to be. In magnitude, we usually show kind of absolute value signs here. So when adding vectors using trig, we're going to break each vector up into its x and y components. Let's go ahead and get this aligned to the left there. Now, you're going to break each vector into its x and y components in a table. But first, let's look to see how to break vectors into their x and y components. You guys could do that using your mathematics, but let's just kind of take a look. Let's just say there's a resultant vector here, and there is an Rx, and here is an Ry, and we always have the angle with a positive x-axis, almost always in physics class. So if we were to wanted to find Rx, how would we do that? Well, we know that if we typically have the hypotenuse and the angle. So if we're trying to find Rx, we know we have, here's our angle, hypotenuse, adjacent. We have cosine of theta is adjacent over hypotenuse. To find the adjacent, we'd multiply the hypotenuse on both sides, the hypotenuse times the cosine of the angle. So if we want to just look at vectors, the adjacent is going to be the x component. The hypotenuse is going to be the magnitude, so do this, of the vector times the cosine of the angle. So the x component is going to be the vector times the cosine of the angle. Likewise, the sine of the angle is opposite over hypotenuse, and we can find the opposite side is the hypotenuse multiplied by both sides times the sine of the angle. So we get the opposite is the y component times the magnitude of the vector times the sine of the angle. This always works if the angle that you're referring to is from the positive x-axis, meaning it's always from this axis right here. Now, you can do it from the negative x-axis as long as you're dealing with the negative signs properly. So this is your y component. Okay, so let's go ahead and make a table with those same exact values that we had before. Go ahead. We're going to bring all of these over. We'll bring them over to the other side over here. And we're going to make a table. Our table is going to have our vector, the x component, and the y component. Vector A is going to be 10 newtons at 110 degrees. So we're going to say the hypotenuse times the cosine of the angle. So we can actually put 110 degrees in there if we want to. Notice we're going to have to deal with some positives and negatives. And so before we go too deep, let's try to figure out if the x and the y component are going to be positive or negative. 110 is over here. In the second quadrant, we know the x is going to be negative, the y is going to be positive. Negative and positive. Now if we do the b, we notice that both the x and the y component of b are going to be positive. For c, we know it goes in the positive direction for the x component and the negative direction for the y component. Now we know we're not going to have issues with our negative signs. So when we take 10 times the cosine of 110, we're going to get negative 3.4202. Notice I'm keeping quite a bit of my digits here for significant figures. I will round later, otherwise we'll have rounding errors. So if I take 10 times the sine of 110, I'm going to get 9.3969. And I do the same thing for my b vector. Here's my bx, here's my by, positive, and my cx, and my cy. Then we are going to extend this table just a little bit further and find our resultant vector. Just the vector when we added everything together. So we're going to add all of the x components up separately from the y's, and we get about 26.4851. All these are newtons, so we can just go ahead and put newtons up in the top column so we don't have to have the units further down lower to complicate things. Okay, so we added all of the columns up in the x and the y. Then we have our x and our y, so we have a pretty long vector in the x, and it goes up a little bit in our y. Our x is 26.49 approximately, and our Ry is about 8.053 newtons. And so our resultant really kind of looks like this here. Let's take a look at our vector we did earlier, and that's what it looks like from before. Okay. So we know that when we add it up graphically, it looks fairly similar to the one where we added with our mathematics. So if we look up here, we have broken each vector into its x and y components in a table. Then we added the x components and the y components separately. Now we need to find the magnitude of the resultant vector. So that's going to be using our Pythagorean theorem. So we have a resultant vector. It's going to be square root of rx squared plus ry squared. So I'm going to put these values in, put the values with the more significant figures in there, and we get an answer of 27.682 newtons. Now we can go ahead, since we're not going to be doing anything further with it, we can tone it down to, we originally had two significant figures, but it was trigonometry, and so when we use trig, we usually add another significant figure because we're not as precise as they are in chemistry with significant figures, because trig does make a difference here. So now we want to find the angle. The angle is, well, if we're looking at something like this, and we have two legs of a triangle, we're going to use inverse tangent to find the angle out itself. So we have the opposite over the adjacent. So we make sure you use the more precise measurements when doing this. That's why you kept the precision, so then your angle would be properly found out. And we end up with 16.91 degrees. Really, we can go down to about 16 degrees on that. You can go down to two significant figures. If you'd rather go 16.9 degrees, that's okay as well. So now you have your resultant vector. Your resultant vector is 27.7 newtons at 16.9 degrees. So you know, oh man, that's bad. Just a second. That would not round to 16 because we have a 0.9. That would round to 17. Take note of that. Don't truncate. Make sure you round. Here's our resultant vector. So it is 27.7 newtons at about 16.9 degrees. So that's the direction the object will get forced.